Humanity has always had a strange fixation on outer space, at first for curiosity's sakes, then for the necessity of humankind, and finally for the sake of showing up his neighbor. Still, there has always been one problem: the mathematics. If our world had been one large, arduous education, then putting a man on the moon was one of the greatest applications of our mathematical knowledge ever. If you would, the greatest science project in existence.
I don't know why I love you, but I do. I don't know why I cry so, but I do. I only know I'm lonely and that I want you only. I don't know why I love you, but I do.
It's one small step for man,
Because I feel so
one giant leap for mankind.
There are many famous scientists and mathematicians involved. One such man was named Sir Isaac Newton. Newton was an English mathematician born in 1643. Newton contributed many things to the world of science, but most importantly, at least for the Apollo missions, he gave the world the gift of calculus. And the book Principia Mathematica.
Do something.
Calculus was divided into two sections: differential calculus and integral calculus. Differential calculus was important because it was the study of instantaneous rates of change, aka acceleration and velocities. This comes in very handy when you have to accelerate a spacecraft and its occupants to a speed of 25,000 miles per hour in a very short period of time, without killing them. Integral calculus was important because it was a concept that calculated an area underneath a function. This has a wide variety of applications in the fields of engineering and came in very important in figuring out how on God's earth are you going to make something that can fire itself and its occupants into the sky at 25,000 miles per hour in a very short period of time without killing them or blowing the device to shreds. If this wasn't enough, he also made the writing Principia Mathematica, loosely translated mathematical principles. This book developed the basic mathematical principles of forces in the world around us. One of the most important aspects of Newton's contribution to math and physics were his laws of motions. From it we can derive that force is equal to mass times acceleration. Moving on.
I've gone through 12 years of education, and I didn't understand a single thing that you just said.
Really?
Not a clue.
Maybe we should look at this a little more in depth.
Maybe.
Fine.
Homage Productions Education proudly presents Math 31 Project. How do we apply Newton's laws and calculus to rockets so that you in your 12 years of education have a clue? We'll start out very simply. This is a Cartesian plane. This is quadrant 1. We use said plane and said quadrant to graphically represent a relationship between two numbers, like input and output. Put in a number and another comes out. Get it? Let's take a simple equation, d equals 1/2 ag squared. We are showing a function, distance as a function of time. If said function is equal to distance, then we might ask, what is the derivative for t? Using simple mathematics that we have learned in the classroom, we simply find that f prime t is equal to at. We also know that velocity is equal to at. Therefore, the function of time's derivative is velocity, which would look something like this. We may have more questions though. What is the second derivative, ft? Quickly, we learn that it is simply a without a t. This means uniform acceleration, which looks something like this. Unfortunately, life is seldom so simple. These rockets did not uniformly accelerate. Instead, change in acceleration was uniform, but not acceleration itself. If we go backwards, this gives our acceleration the same slope as the velocity. We can further derive that, in fact, the velocity takes the shape of the distance time graph before. It is in the shape of a quadratic graph. We also see that now the distance time graph looks more like a cubic. We know this is true because if we followed the original uniform acceleration graph, the astronauts on the Saturn V rocket would feel about 3 Gs, or about 3 times heavy as they do if they were standing on the ground. We actually know that the rocket at its climax would accelerate at 90 meters per second squared. This is the equivalent of 10 times the weight of gravity. So, using simple principles of calculus, we have determined how to apply calculus to a rocket. Voila! Calculus and Newton with rockets.
Really upset.
Go.
Now do you get it?
No!
Good for you. Moving on.
We also take that all motion, energy, and force is conserved. That means when the ship accelerates from the Earth, the flames and propellant accelerates backwards. The people accelerate forwards and they are forced back. This comes in very important in the design, process, and training cycles. Newton also came up with a very interesting idea. We call it orbit. If we can accelerate an object fast enough so that its trajectory matches the curvature of the Earth, it will remain there forever in a state of free fall. He wanted to use this mathematic relationship between x and y vectors on a cannonball, but obviously it had other applications. One such example was Sputnik 1, the first artificial satellite network, a great mathematical and human achievement. There was only 2 problems. All it could do was beep like a broken alarm clock, and 2, it was Russian. The Americans were awestruck and now they were determined. If there was a race, they would run. So Newton has given us our principles and our math. Without them, essentially we are lost, but even with them, it is doubtful that the Victorians could launch a V2 rocket, let alone a Saturn V. Newton gave us our mathematical clay to play with, but it took another very important mathematician to give us our form. Konstantin Eduardovich Zolsky was a Russian born in 1857. Born into the Russian Empire, he would live through the Russian Revolution, World War I, and the beginning of the Great Depression. Seeing all the devastation, surmised the colonization of outer space in an attempt to preserve humanity. He was the first to conceive of a space elevator after he witnessed the constructed Eiffel Tower, but mostly he believed in rocket propulsion. So that's what he did. He spent his life working out the math for rocket-powered space travel. He began working on calculations for lighter-than-air spacecraft, the same one done by the Wright brothers on the other side of the ocean, and then moved into rockets. His greatest contribution to math and science was the Zolsky rocket equation. This used conservation of momentum. Essentially, it was a mass ratio by rocket propulsion that brought in all of Newton's laws for one simple calculation. It took years to develop and was the lifeblood for all rockets, especially multi-stage ones that hadn't even been practiced in large scale yet. There were only 2 problems. Humanity didn't yet know how to use rockets for lifting large payloads, let alone multi-stage rockets. And 2, he was Russian. Seeing a pattern? Because he was Russian, no one in the Western world knew of him till the 50s and 60s, 30 years after he was dead. This doesn't mean he doesn't deserve our attention though. NASA was so appreciative of his work that 30 years after he died, they translated everything he ever wrote, and most of it was still futuristic. He also got his head on the Russian rubble as the founding father of space. There are only 2 more characters in our harrowing tale that made it the essentials in mathematics for Apollo 11. The first was named Carl Jansky. Jansky was a physicist and a radio engineer hired by Bell in 1933 to figure out what was interfering with their radio waves, in effect using the mathematical principles of the time, and built the world's first radio telescope. It was 100 feet long and stood on Model T wheels. What he discovered changed radio mathematics forever. It wasn't disturbances in the sky, it was the sky, more specifically radio waves broadcast from outer space itself. The radiation from the sun was in fact partly causing radio waves. The development of this not only let scientists map the sky using complex logarithms to tune it in, but allowed the construction of massive telescopes around the world. One was in Australia. It was called Parkes. Parkes is essentially what we would call a satellite dish that is 64 meters in diameter. It is one of the largest in the world and is located on the opposite side of the world as the ones in Australia. Maybe we should take a break to explain how our universe works. The moon goes around the Earth and spins to always face the Earth. The Earth also spins on its axis while going around the sun, which is possibly moving around something else. So for the spaceship to travel from the Earth to the moon, it has to also orbit the Earth, and to do this, it must have an uplink on the other side. This is where Parkes came in. It was powerful enough to tune into almost any frequency and could amplify 100 billion times. Used in combination with many other scopes, not only does this pick up the signal, but by using trigonometry, locations can be checked, time saved, lives saved, and more importantly, television broadcasting. We'll come back to that later. Only one man left, Wernher von Braun. Braun got out of university during a very rocky period of German history. A certain political party had been elected. Rockets were forbidden by civilians, and so Braun worked for the military. Progress was very laborious, both the thruster and the guidance system. Sadly, the rocket parts that were designed with travel in mind were used for other means. He described the day that his rockets were used as his darkest day. Anyway, the war came to an end, and to show no hard feelings, a certain government hired him to work in one of their new organizations. His job was to help get a person into space before the clockmakers on the other side of the planet. The goal took a lot of work, but even more resources. Apollo was an achievement of mathematics in every way. One of the largest buildings in the world, the VAB, was built for it at 128,428,000 cubic feet. The first rocket launched burned for 2.5 minutes, lifting the rocket 60 kilometers and to a speed of 9,921 kilometers per hour, burning 4.4 million pounds of propellant. The next stage then exploded to life burning for 6 minutes, pushing the ship 178 kilometers away and 25,182 kilometers per hour. That's about 7 kilometers per second, or the equivalent of going to Edmonton in a little less than 30 seconds. They had done it. Using Newton's laws and calculations of t, they had traveled 25,182 kilometers per hour, or enough to get out of the Earth's gravity. 38 seconds later, they pulled into a close loop to take a run around the planet and then slingshot at the moon. The third rocket then kicked in for 2.5 minutes. This pushed the rocket to approximately 26,000 kilometers from where it started at an altitude of 188 kilometers and a speed of 7,790 meters per second. There was one more barrier that they had to get through. They had to leave the Earth. For good. They came around the Earth in 2 hours, then they put the pedal to the metal, and the rocket reached a speed of 14,320 kilometers per hour. After that, they were on their own. Only the relay dishes on Earth kept them in contact. 3 days later, the LM split from the CM, which could continue to orbit the moon. This was the most dangerous part of this trip, and it showed. This was the one spot where everything went wrong. Firstly, the computer in the ship, stranded with all the calculations it was doing, stopped on overload. Then they overshot their landing spot. Suddenly, an alarm went off that scared everyone. The 20 seconds of fuel alarm went off. When they touched down, they had 6 seconds left. Using the dishes developed decades early for radio observatory, Parkes connected to the Westinghouse camera, and 500 million televisions instantly broadcast to the first man on the moon.
Columbia, this is Houston, AOS, over. Columbia, over. Roger, the EVA is progressing beautifully. They're setting up the flight now. I guess you're about the only person around that doesn't have TV coverage of the scene.
1, 2, 3. 1, 2, 3. Ow! Say it one time.